Okay, I want to talk about a vector field. Okay, the idea of a vector field, you can just imagine 2 or 3-dimensional space just full of vectors. There's a vector at every point. That would be a vector field. Now, they got a little more concrete. Let's say we have a positive charge here. Then, at any point in space, if we put another positive charge at that point, that positive charge is going to be repelled straight away from this charge. Now, if we put the same charge at a lot of different points, well, the further the charge is away from this, the less force is going to be exerted on it, the less repulsion there's going to be. And it's going to fall off as, well, it's going to be a reciprocal square relationship. It's going to fall off as the square of the distance. So we could draw a couple of concentric circles here just to indicate approximately what happens with this vector field. Okay, then we'll take, I'm going to draw a line. I'm going to draw lines at 45-degree increments, pi/4 radian increments, around this charge. And I'm going to then draw an arrow here that indicates the degree of repulsion you would have, the amount of force you would have on this other positive charge. Okay? It's always got to be straight away from the charge. It's radial, in other words. And it's going to have the same magnitude at every point on this circle. Not a very good circle, but you can kind of correct that in your head and imagine there's a good circle. So all these points are going to have a charge of equal magnitude, or a force of equal magnitude, but of course the direction always being away from the central charge. So in a sense, these vectors diverge from this charge, and that's going to be an important word. I'm not going to do much with it today, but kind of keep in mind that this is a field that's diverging from this point, because one of the most important concepts in this chapter is what's called divergence. So kind of store that away. Okay, well, now we go out to this second circle, which is about twice the radius of the first, and the force is still going to be straight away, but it's going to be 1/4 as great, reciprocal square. And you can kind of think of that as the sphere surrounding this thing at this distance has 4 times the area of the sphere that surrounds it at this distance. So the effect of this charge is, in a sense, distributed over a sphere of 4 times the area. So it's going to be 1/4 as great. And that's kind of an important insight for what we're getting into. So here we have it. Okay. Now you can imagine what the rest of the field would look like. And of course we can fill in arrows in between these and so forth. But it's a field that's radial and decreasing as the square of the distance. Okay? You can imagine a velocity vector field of a water flowing down a drain. Well, you don't have curvy vectors. But, okay, here's the center of the drain. Your vector field might look like this. Water's flowing at a certain rate, more or less in a circle here, and at a little less rate in a circle out here. Now, this is not going to necessarily be an inverse square because the geometry of the situation is much different, but we get the idea. So you've got a kind of a circulating vector field here. So this is a diverging field. This one doesn't diverge, this one circulates. So diverging field and a circulating field. And there's a quantity that you associate with the circulation of a field called the curl. Very easy to calculate the divergence of a vector field, or the curl. You just use a del operator, just the same operator used for gradient. And you dot the thing with this field, you cross it with this field, you get the divergence in the curl, and it gives you the degree of circulation or the degree of divergence. Okay? That's just a foreshadowing. Don't worry about it. Now, the thing, the kind of crux of this whole idea of vector fields and the calculus you can do on vector fields, which is the main thrust of this course. Everything else kind of builds up to it, even though there are very important things that happen before we get to vector fields. Okay, very important applications. You've seen many of them. And some very interesting mathematics. It gets really interesting here. And there's this thing called Green's theorem. Now, I would not introduce Green's theorem this way to a typical class. And I've never done it this way before numerically. I've always done it symbolically because it's so much easier. But let's try to understand what's going on here. Okay, so we've got a vector field. And a vector field in 2 dimensions, just a vector field in the plane. And we'll kind of extend this to 3 dimensions, but there's some things we need advanced calculus to extend into 3 dimensions. Still, we're going to do most of it, okay, in 3 dimensions. But in 2 dimensions, you have a vector field. And it's just some function of x, y times I, some function of x, y times j. Okay? I'm not going to specify a field, I'm just going to write down some numbers. So here I have a rectangle in the plane. It doesn't matter what the coordinates of the vertices in this rectangle are. All that matters is the value of m of xy and n of xy at the corner points. Now there are other things that matter, but we're going to focus just on this. So at this corner point, m is 2 and n is 3. At this point, 2 tenths of a unit in the x direction from this one. M is 2.2, n is 2.7. And similarly, we have m and n at this vertex and m and n at this vertex. Okay, well, we can calculate the approximate partial derivatives of m and n along each of these sides, edges, that's the word I was that's the word I was looking for. Okay, so along each edge, we could calculate average values of n and m. Now we're not actually going to use those values on the edges except to get an average value of the x derivative of n and the y derivative of m within this rectangle. So let's see how that works out. Well, if we go from here to here, the value of m changes by 0.2 and x changes by 0.2. So the average of mx is 1. And the average of nx is negative 1.5, very easy. N decreases from 3 to 2.7, decreases by 0.3, changes negative 0.3, you divide that by the delta x, and you get your average value of nx. And we just do that on every edge, okay? And I think I've calculated these right. It's the reason I wrote it out in advance so I wouldn't be fumbling and making stupid mental mistakes. Okay, and everything seems to work out the way it should, so I think maybe I've got the numbers right. Okay, so anyhow, and from those values, we just take the nx we have along the lower part of the rectangle and the nx we have along the upper part, and we average them, and we get negative 2.25. And we take the average value of my over these 2 edges, And we have -2 and -4/3. That averages out to -1 2/3. I went ahead and made it a decimal so I can do decimal approximations. So there we have it. Now, this is not really the average of nx, and this is not really the average of my because of the way the function changes within the rectangle. But it's a small rectangle, and these values don't change by much from corner to corner. So we expect we've got a reasonably good approximation if we've got a non-pathological function, a function that's relatively smooth. Okay, so we have our nx bar and our my bar. So now we can talk about the integral of, sorry, wrong integral, the integral of, I didn't talk about it. Well, let me go ahead and do it. Okay, well, the double integral of nx minus my with respect to the area, and watch me have gotten this wrong, but I think it's right, is what? It's approximately equal to, well, it is equal to nx bar minus my bar if you have the actual average values over area of these quantities times the area, which is 0.03. Okay? And the area is easy, 0.2 times 0.15 is 0.03. Well, then that's equal to nx minus my is 0.58, negative 0.58. Negative 0.58 times 0.03, and that's equal to negative 1.74, 0.174. Okay. Now that's easy. Now let's approximate the line integral of m with respect to x plus n with respect to y as we go from here to here to here to here to here. In other words, as we make a complete loop around this rectangle. Okay? Well, that's very easy to do. And at this point, I think you might not have seen line integrals, but the idea is actually very simple. Okay? The average value of m from here to here is 2.1, because it goes from 2.2 to 2.2. Now you don't know that's really the average, because this thing's not going to be linear, but small interval, you expect it's going to be close to its linear average. Okay, so the linear average is 2.1, you multiply that by 0.2, and you pretty much get the integral of a quantity that goes from 2 to 2.2 over a distance of 0.2. So if this was a segment of the x-axis, you'd be multiplying the average value times the delta x. That's all we do. So that the integral of m with respect to x from here to here is just approximately equal to the average value of m times delta x, which is 2.1 times 0.2, 0.42. Okay? No big deal. Now I'm going to skip up here and say, okay, well, now I come back the other way because I'm going around this loop, and my value of m, my average value of m, is the average of 1.9 and 1.8, which is 1.85, and we multiply that by the negative 0.2 x increment, and we get negative 0.37. Okay, so, and you know, the values of m are less up here than they are down here, so clearly the average value of m is going to be less. The displacement is equal and opposite, giving you the negative sign as opposed to the positive here. The numbers aren't that much different because these numbers, here and here, here and here, are not that much different. They are different, and we'll talk about why they're different and just, you know, the subtleties of why this gives us the astounding result that we get. And it really is kind of astounding, especially when you expand this to arbitrary curves, but arbitrary simple closed curves. Okay, so well, we do the same thing with n, and you can verify the calculations. The average value of n here is 2.85 between here and here. You multiply that by the displacement, 0.15, you get 0.4275. Maybe I'm right, maybe I'm wrong about that, but I kind of think it's right because everything worked out so well. Okay, and then over here we do the same thing. So we get the integral of n with respect to y, 0.4275 on this edge. And now on this edge, where we have a negative delta y, we get negative 0.495. So that the line integral, the summing up of all the m values from here to here, all the n values from here to here, all the m values from here to here, all the n values from here to here, all the values with respect to distance along the edges, should be pretty close to this plus, well, let's look at it this way. This plus this, because that's how the m integrals change, and this plus this, which is how the n integral changes. So we just write down those numbers, add them up, and look at what we get. And compare this with this. Now, why in the world should the summing up of the values of the function, the m function here, the n function here, the m function here, the n function here, the summing up of the values of the function with respect to distance, which is what the integral is, give us an integral over the area of the x derivative of n minus the y derivative of m. Why in the world? Okay, well, I can explain that, but I'm going to let you think about it. I'll explain it next time.